All right, it's my pleasure to introduce Dr. Mohammad Ali, maddah-Ali. I'm glad he could make it. He told me he was flying via Qatar, and I don't know if you know, but now all the countries around Qatar are stopping flights going through them, and so we were worried he would be able to make it or not, but now he's here. Yeah. So Dr. maddah-Ali has, well, he graduated from the Isfahan Institute of Technology and then the University of Tehran, got a PhD from the University of Waterloo, and since then has worked in a variety of industry positions, but had a postdoc. He's been at Nokia Bell Labs as a research scientist since 2010. He's got a whole variety of Best Paper Awards or equivalents of that, including things related to what we'll be talking to us today about.
Thank you very much, the organizer, for inviting me, and thanks for the nice introduction. So today I'm supposed to talk about cache networks, fundamental trade-offs, opportunities, and challenges. I changed the title a little bit to be able to. Oh, yeah, I changed the title a little bit to be able to cover some of the recent results that we have. It's related, it's not far away. So I changed it to communication, computation, and storage. It's a little bit too, big subject, but I hope I can cover some interesting stuff. But still, to be able to, fulfill my promise, I will spend the first 3 sessions on caching, and the last one on compute. So if you are interested only in caching, you can stay for the first 3. And if you are interested in computing, you can come for the very last session. This is a joint work. I had many collaborators. I have been working on this topic for about maybe 4 or 5 years now. The first collaborator is Urs Nielsen. Most of this stuff that I'm talking about on caching, it was in collaboration with him. Also, Salman Al-Estime, he's a professor at USC. Some of the stuff on caching is with him too, but the stuff on computing, all of them was with him and his students. Suhas Sigavi from UCLA, UCLA. Ramtin Pedarsani, he's now a new faculty at UC Santa Barbara. Navid Naderi Alizadeh, he's now in Intel. Nikhil from IIT. And Tian and Sangzi, both of them are now PhD students at USC. So during the talk, feel free to stop me anytime that you want if you have a question. Make it interactive as possible. So, the infrastructure for big data, it has 3 major components. The first one is computing. The other one is communication. And the third one is the storage. We know, over the last few decades, we have seen enormous progress between each of them. We know how to do computing, we know how to do communication, we know how to do storage. What we don't know is how these interact with each other. So within each of them, we are good. Interaction is where we are limited. Our knowledge is very limited. So in this interaction, there are a lot of open problems. Okay? Especially if you think about constraints that we have, like delay, energy, privacy, security, fault tolerance, cost, universality, and scaling. And so the question is, why don't we solve this problem? What is the main challenge to solve this problem? Can you guess what is the challenge? Any guess? So I'm claiming there are a lot of problems, but so why not solving them? It is hard, but the challenge, there is another major challenge, or first challenge. maybe. What else? The challenge is how to find these problems. These problems are hidden in this, universe. It is very hard. The first challenge that we have is to find the right problem, the problem that gives us non-trivial solution, give us right scaling. So, not just for you students, for even senior researchers, finding the right problem is the first challenge that we have in this area. And one reason is that these problems are not like within one discipline. These are multidisciplinary research. And so to work on these problems, you cannot just stay within your discipline. You have to talk with many people and understand some other fields to be able to find or formulate the right problem. So one thing that I ask you to do in this maybe workshop is to not just focus on the solution and the beauty of the math behind it. I want you to think about how we can find the right problem in this area. Okay, so based on what I said, in this talk I will cover two areas. One of them is cache networks, the other one is computing. For cache networks, first I will talk about motivation. Then I will review some of the results on single cache networks. Then I will cover multi-cache networks. And in the multi-cache networks, first I will talk about a very basic network, which is called bottleneck network. Then I will generalize some of the results to general networks. Then I will connect caching to wireless communication. And I will talk about cache-aided interference channels. Then we will move to coding for computing. And for computing, first I will talk about how we can use coding in the MapReduce framework. Then I will talk about some of our very recent results on using algebraic coding for massive matrix multiplication. And at the end, I will talk about communication-aware computation. So these are the topics that we will cover. Any questions so far? Okay. So part one, cache networks. Let's start from motivation. There are a lot of reports on how the traffic in the network is growing, which is exponential. All of them agree on this. And all of them agree that video takes a major part of it. This is for wireless from Cisco. And as you see, it's growing very fast. And major driven for that is video. For example, 3/4 of the traffic is by video. Here you can see. This is for wireline. Again, we see the same trend. And so, for example, even now, Netflix and YouTube, they take about half of the traffic in the peak time. How we can solve this problem? We can use the temporal behavior of this traffic. This traffic, in the early morning, the traffic is very low. In the afternoon, in the evening, the traffic is very, very high. And so we have to design the system to be able to cover the peak. But when the traffic is low, we have some resources left to be used. In caching, we can, to solve this problem, we can use cache. So when the traffic is low, we use the memory is distributed across the network to store some of the content. And in the peak time, we use this content to be able to deliver the content with less traffic. So we can move in this peak to this underutilized area. This is the idea of caching. So let's go through several examples. The first one is Netflix. These days, ISPs can use Netflix caches. It is operated directly by Netflix. These caches are about 100 terabytes, which is like 4 years of watching video. And so each night, the Netflix uses the low traffic time, 2 a.m. to noon, to update these caches by about 7.5 terabytes of data. So every night, when you are sleeping or when the traffic is very low, early morning, the caches are updated. These caches are reduce the traffic about 60 to 80% of the, they reduce the traffic 60 to 80%, which is a large reduction. The second famous example is Akamai. The network that we know is, consists of about 100,000 autonomous networks. Some of them are big, some of them are small, and they are connected through like peering links. And what happened is that for some economic reasons, these links become bottleneck, okay, because none of them wants to carry the other network traffic. So Akamai uses about more than 100,000 caches, put it in these networks, and these caches will reduce the traffic in the peering link, and also, it reduces the traffic from the origin server, and this way, it helps the system a lot. The other one is Facebook. Facebook uses several layers of caches, from browser cache, edge cache, origin cache, and backend cache, to store the pictures that you are downloading, and to reduce the traffic in the system. The very recent one is, this one is recently getting very popular, femto cache. This one, right now, cellular system is like this. We have big cells with big base stations that covers a large area. To improve the performance of the system, we may use several small femtocells, which are a small, let's say base stations. The problem with these femtocells is that their backhaul link is weak. And to reduce the traffic in the backhaul link and improve the delivery delay, we may use cache in these femtocells and improve the overall performance. This is another application. There are more applications. I have it in the back of the slides. You can see it. I already uploaded the slides in the system. So in all of these, the main question is how to run these cache networks, what to put in these caches, and how to update them. And the solution would be very different if we have a single cache system and multiple cache systems. So from ATs, we have a lot of results on single cache networks. And here we want to say that for multiple cache networks, the story is very different, and coding and information theory can help a lot. So these are the references that you can go, and now we move to the second part, which is single cache systems. Can you change this size?
Here.
Okay, so maybe I should have continued with the previous one. You see, that's okay.
Sorry. Let me change the. Which part?
Single cache.
This part too?
Single cache. Yes.
Yes. Okay. And use this screen.
Thank you.
Yes.
Okay, so this is the first part. This is the second part. The first part was motivation. So here I just review some of the results on single cache system very fast. I don't go through the proof. I just review some of the results to prepare ourselves for the next part, which is cache networks. So consider a system like this. We have a server, we have a cache, and we have a user. The server has some files. Here it has just 3 files, blue, green, and red. The cache has a space to store M of these files. So in the real system, it could be hundreds and hundreds and thousands of movies here. But here I'm just in this picture, I have just 3 files. Here the cache has a space on storage limit. For example, in this picture, I have only 2 files to store. And then we have a user. The user requests a sequence of files. Okay? For example, here it asks for the red file, blue, red, green, and so on. And in response to each request, the server has to send something such that each user is able to see the file that is asked for. Okay? So in response to each request, the server has to send something. What is the main objective? Our objective is minimize the load of the server here. We want to minimize the traffic here. Okay? What are the design parameters here is how to preload this cache here, what to store in this one, and how to update the content of the cache. Okay? So we have two scenarios or two questions to be answered. One of them is at the beginning what to store here, and the second one is how to update the content of the cache. To answer this question, we need to first understand what is our model. Okay? So the answer would be very different depending on the model that we have. Okay? And also, it depends on the definition of the load here. What do we define the load of the network? If we care about the peak load, then the answer is something. We may care about the average of the load here. So we assume that these requests are coming from a distribution and want to minimize the expectation of the load here instead of the peak. This one is called independent reference model. And we want to, another scenario is, we care about every single sequence. So no matter what the sequence here, we want to have a good load here. So we don't want for any sequence that our load is far away from us. And this is called individual sequence model. These are three different approaches. In computer science, mainly we focus on this one. In system, we may focus on this one. In information theory these days, we focus on this one because it is easier to understand. So all of these three are valid, model and question. So let's start with the easier one, which is the peak load. So in this case, as I said, let's assume that in the server we have n files, and the cache has a space to store m files. Okay? And what we want to do, we want to minimize the peak of the traffic here. So for different requests, the load here would be something, and we want to minimize the peak here. We want to minimize the peak for every different request. Can you guess what should be stored here? Any idea?
N over M from each file.
M over N from each file. Why?
To satisfy the cache storage.
And minimize the peak. So we should, very good, that's correct. So we should be ready for every possible demand, okay? And minimize the peak. So we don't care about average. Here we want to minimize the peak. So for every single demand, we should be good. So in this case, we can take the first M over N fraction of each file. Together they are M files, and store it here. Okay? Then, for example, if the user asks for the blue file, we need to send the rest of it. And the rest of it is 1 minus M over N. Okay? So the peak traffic is 1 minus M over N. The unit here is 5. Okay? So if the user asks for the red one, we need to send the rest of it, so it will be, again, 1 minus M over N. So for all possible demand, the load here would be 1 minus M over N. Because M over N fraction of each file is available, we need to send the rest of it. And it is optimal. Can you guess why? Can you come up with an information theoretic proof that this is optimal? So I leave it as an assignment for you. Okay. So we can prove that this is optimal, and we cannot do better than this. Okay. So do we need to update the cache content? This one was prefetching. This is how we fill the cache at the beginning. How should we update it here? We don't need any cache update. This is just, we keep it as it is, and it is optimal. So cache updating is irrelevant. The second one is if we care about the average. So we assume that there is a known distribution, which is known beforehand, and the user asks files with this distribution independently over time. So the distribution is fixed, over time it's fixed. Each time independently we ask for a file according to this distribution. And what we want to do is to minimize the expectation of the load in the bottleneck. What should be stored this time? Anyone? It shouldn't be difficult.
What is the highest probability?
Exactly. So here, as I said, we can store M of these files. Some of them are more popular, some of them are less popular. The distribution is known and is fixed, and each time we identically and independently request the file from this distribution. So the answer is we should store the most popular files. The M most popular files we store. And again, we don't need to update the cache. So prefetching is this one, and cache updating is not needed. And it is optional. Okay? And again, there is another assignment for you to prove information theoretically that this is optional. This could be a little bit challenging, even though it looks very, trivial. But proving it is not that straightforward.
What if you put parts of the file but weighted? I mean, the size of the parts would depend on the probability.
It's not optimal. So in this formulation, I'm allowing to chop the file into smaller pieces, and you are allowed to store not only a piece of file, you are allowed to store any function of the file. Okay, and still this one is optimal, and you can prove. Okay? So if you couldn't, ask me later. Okay, so these two are like easy cases. Now let's assume that again the sequence of requests are IID, but we don't know the distribution. The distribution is unknown beforehand. What should we do? Any guess? So distribution is fixed, but it's unknown. Any idea what to do? Just say something. If you don't have enough space to cache everything. The oldest part. What else?
Estimate the distribution based on there is something we saw before.
Exactly. So one approach is to try to estimate the distribution based on the history. Okay. This is called, it's called least frequency used. This is the one that we evict. So we store the most frequently used one. How we calculate the most frequently used one? We keep track of the number of times that each file has been requested. Okay, and the most frequent one is stored in the cache. And if someone through the time became more popular than others, we evict one of the least, frequently used and replace it with the new one. We just learn the care. We just learn the distribution. This is the solution. Okay. So the first one was peak. This one was the second one was average. Now the challenge, what is this? This is a kind of interesting challenge. The challenge is that in the real world, the requested files over time are correlated. Not the files are requested are correlated. The requests are correlated. Okay? So when a file is getting popular, more people will ask for it. So the requests over time is correlated. The second one is that these popularities are changing over time. These are not fixed, they are changing over time. And actually, we may not be able to fit any probabilistic model to this request. Okay? This is the challenge that we have. So here, you can see, the curve of popularities that we extracted from Netflix prize data set. What we see here is that as soon as a movie has been released, it became very, very popular. And then over time, it lost its popularity. Again, a few weeks later, another movie has been released. It became very, very popular at the beginning, and over time, it lost its popularity. So you may not be able to fit any model to this one, and so you don't know how to use it. So in this case, what is your suggestion? How should we update our cache content? Anyone? Any guess? Any suggestion?
I think least frequently used in the last week.
Very good. So we may focus on like recent history rather than the entire history, because it is changing over time. We may say, let's focus on the last week, or let's focus on the L last requests. But how should we choose L? Should we choose it as a fixed number? Should we change it adaptively over time? It's very hard. You may come up with some solution for this, but there is a very beautiful solution that implicitly does this, and this is called least recently used. The least recently used is like this. Every time that the user asks for a file, and that file is not in the cache, okay? What we do, we evict the least recently used, the oldest one in the cache. We just evict it and replace it with the new file. So that file has been requested. We look at the cache. If it is in the cache, we deliver it. If it is not in the cache, you have to get it from the server, yes? No, so it's not available in the cache, you have to get it from the server. So you have a cache miss. In this case, you first update the cache content. How? You evict one of the files and replace it with the new file. Which file? The oldest one in the cache. You evict the oldest one and replace it with the new file. Okay, so here, for example, let's assume that in the cache we have the green and the red file, and the oldest one, least recently used, is the red one. And then assume that the user asked for the red file. So here, because it is already in the cache, we deliver it from there. But at this point, red file is not the oldest file. We put it up there, and we put the green file here, because now green file is the oldest file. Now here, blue file has been requested. It's not in the cache. It's not in the cache. So we evict the green file, but we put the blue file here. But now the red file is the oldest one. Now orange file has been requested. We evict the least recently used file. We put it here. The blue becomes the oldest one, and so on. Okay. So here we are not counting how frequently we are using the file. We are not adjusting the history, short history, long history. But still, this algorithm performs very, very well. Okay? But the question would be how to measure the performance of this system, this algorithm, how we measure the performance. What we do, we compare it with an offline algorithm. What is offline algorithm? In this offline algorithm, we assume that the cache memory already knows the sequence of demands in the future. Okay? So for example, beforehand, it non-causally knows the future. It knows that red file will be asked, blue file will be asked, blue file, and so on. So you know the future. Okay? So we will compare LRU with the performance of optimum offline algorithm. Okay. So can you guess how should we update the cache content if we knew the sequence beforehand? So you know what's going on in the future, and now a new file has been asked. You want to put it in the cache. Which file you evict? Future. So we look at the future and see which of them is less used. What else? The farthest one in the future. So there's an algorithm called bloody algorithm. It says that each time there is a cache miss, you need to evict the one that has been asked farthest in the future and replace it with the new file. Okay. So here the algorithm is based on the future apparently, so it's not practical, but it can be used as a baseline for us. So for example, say the green file and red file are in the cache, and the red file is requested. So here we don't change anything because the file is in the cache already. So we fetch it from there. So the cache remains the same. Now blue file has been requested here. It's not here. I need to evict one of these two files and replace it with blue. Which one I should evict? I see the future, and I see that here I need the red file, and later I will need the green file. So we remove the green file and replace it with the blue file. Okay? This algorithm is based on this assumption that each time that we have a cache miss, we have to replace the file with the new file. Okay? Again, here, the blue file is requested, so we don't need to do anything. Here, the red file is requested, so you don't need to do anything. Again, here, for example, green file is requested, it's not here. We need to evict one of these two files. You see that very soon we will need the red file, so we evict the blue file. Okay. This algorithm is optimal, and to read out the proof, we can look at the the book Algorithm Design by Kleinberg and Pardos. There is a constructive reading proof for this one. But to answer the algorithm that you suggested, you may say, why not store the most frequent files in the cache? Okay. So for example, let's say we will have, I know the future, 100 times we will ask for the blue file, 300 times we will ask for the red file, and 300 times we will ask for the green file. Okay. And so, because you know the future, you would say that because I need these two files, I will store the green and red here. Most of the time, I will need these two, because blue was 100 and these two are 300. So I store the green file and red file here. Okay. How many misses I have here? How many times I need to fetch a file from the server? 100 times, because here I have a cache miss, here I have a cache miss, and so on. So the cache miss here will be 100 times. But if we apply bloody algorithm here, so you can see here I will ask, initially the cache is the same, green and red, and somebody, the user asks for the blue file. I will have a cache miss, and I look at the future, and I see that I will need the green file for this in the future. So I replace the green file with the blue file. So here I have one cache miss. I don't have any cache miss all the way to this point. Okay? And then at this point, Again, we will have another cache miss. So we replace the blue file with the green file, and we are good to go. So this time we have 2 misses. Okay. Any question?
What is exactly the character? What optimal with respect to what? Like,
The number of cache misses is optimal. We do 2 assumptions. One, each file is treated as a whole with 1 unit. You don't please make it smaller pieces. 2, each time that we have a cache miss, we have to replace the file with the new file. Okay? With these 2 assumptions, it is shown that it is optimal. Is it optimal generally? I don't know. Do we have an information security proof for that? We don't know. But considering these 2 assumptions, this is optimal.
So the number of misses would be growing with, so it's like based on a fixed number of demands, right?
Yes. So let's say if the sequence is infinite, there are like, let's say the sequence is very, very large. The number of misses would be very large, but it is optimal. Of course, if the sequence grows, it will be like many, many misses. But this is the minimum possible. And the proof is like this. We say if there is another optimal algorithm and these 2 algorithms, if there is another algorithm which is optimal, and bloody is something, if these 2 are not the same, up to some point, if you see a difference, you will change the optimal algorithm to bloody at that point, and you will show that the number of misses does not increase. So the proof is as there are some details, but the proof is kind of 3D modification of every optimal algorithm. So one problem for you, open problem, I would say, is to prove if information theoretically, bloody algorithm is optimal. Yeah. But we said we had LRU. LRU was based on history. And then we have bloody algorithm, which is based on future. Okay, so you know bloody algorithm, you know the future. LRU was based on the history. Now the question is if these 2 are working closely with each other. So we need to define competitive optimality, notion of competitive optimality. So we say an algorithm, an online algorithm is C competitive optimal if for any sequence of requests, for any possible sequence of requests, the number of cache misses is at most C times as the number of cache misses in the optimum offline. So we have a notion, we have a constant C. If no matter what the sequence is, these 2 algorithms, the number of misses are within constant factor of each other. It can be a function of m, but it cannot be a function of the number of sequence. Okay, the number of the size of the sequence, the length of the sequence. So if this is the case, then we say the algorithm is competitively optimal. Okay? And there is a beautiful result by Slipper and Karjan. You may want to read this paper. It's very, very beautiful. And the proof for this result is very short. So what they prove is this one. Let's assume that I have my original system with the cache size m, and then I have another system with cache size m over 2. And let's say both of them see the same sequence of requests. The requests are exactly the same. Okay? Then we can show, and here, the only difference is that the cache size here is m over 2. Okay? The cache size here is m over 2. So I'm here, my cache is m. Here I'm having, in the offline algorithm, my cache size is m over 2. Okay? In this case, the number of misses in LRU is at most twice of the number of misses that I have here. Remember, here, this one is based on the history. We don't know the future. Here, we know the future. These 2 working very closely with each other. Okay? So if you consider a 2-dimensional pair, one of them is cache size, and the other one is the number of misses. In this 2-dimensional space pair, you are within constant factor of, these 2 pairs are within constant factor of each other for every single sequence. So it's a very strong notion. So this one is maybe the most strongest result that we have for the for this case. Okay. Now I have a question. What is the metric of optimality for a system with single cache? We wanted to reduce the load here, okay? But it was translated to what? To number of cache misses. If the number of cache misses is minimal, then the algorithm was optimal. So we have two different notions. One of them is load of this link. The other one is cache misses, the number of times that you don't have the file nearby. Okay? In single cache system, optimizing these two are equivalent. You don't care if you optimize the load here or minimize the cache miss. What we want to show for cache networks is that when we have more than one cache, this is not the case. So, even now, for cache networks, what they try to do is try to minimize the miss rate. What we will show is that when you have a cache network, it is not correct. It's not right to do, and you need to go back to the load of the server and optimize it from there. And coding can improve the performance a lot. It can give us a scaling factor in the game, which will be the subject of the next class. Any question? That's it for today.
So, any final questions for Professor Mohammad Ali? Well, if not, so people who have not collected their posters for today can do so. Otherwise, we'll be leaving for the poster session. So there'll be two buses going to the beach. The first bus will leave in about 5 to 10 minutes. The first bus will go to iHouse, stop there for 15 minutes, and then leave. The second bus will leave at 4 p.m. and will go directly to the beach.
Or should I turn it off? Yes. Thank you.